There are situations when we need to know how fast a point is moving along the edge of a circle, or we might need to know how fast the central angle is moving. An example of when you might need to know these things is machinery involving gears. We are going to use this given figure with point P and then a given angle on there to help explain these ideas. If some point P, and here's P on our circle, is moving at a constant speed along the circle, so if it's moving along here, just the P, around the edge of that circle, then the measure of how fast P is changing is called the linear speed. Think about when you drive. You talk about how far you went compared to how long it took. I drove 25 miles in 10 minutes. Linear speed is the same idea. Our formula uses V to represent speed. You can think of that as velocity. S is the distance along the circle, so it's your arc length. And T is time. So we have our linear speed formula of V equals S over T. Now we're going to think about ray OP, which is this ray. As point P is moving, then the whole ray is also moving, and that means that this whole angle is constantly changing. The rate at which this angle changes is called the angular speed. We symbolize angular speed with the lowercase Greek letter omega, and it's kind of a funky looking little W. The angle is changing according to the angle measure related to time. So it's so many radians per minute, so many radians per hour. This gives us our formula for angular speed. Omega equals theta over T. Remember, theta must be in radians. Earlier, we talked about the arc length formula of S equals R theta. So if we take our linear speed formula and substitute R theta in place of the S, we get V equals R theta over T. We can rewrite that fraction just a little bit as R times theta over T. We just define angular speed to be omega equals theta over T. So now notice we have a theta over T and a theta over T. So we are going to take out the theta over T and replace it with the omega that it's equal to. We now have the formula that will show the relationship between linear speed and angular speed. The formula that shows the relationship between linear speed and angular speed is V equals R omega, where V equals linear speed, R equals radius, and omega equals angular speed. Our first example where we are going to put all of these formulas into play is example 5 that says a ceiling fan has 14-inch blades. So the radius of the circular fan is 14 inches. If you think about the blades on a ceiling fan, they go from the center out. So they are all, each one, a radius. Then you are told the fan turns at a rate of 45 revolutions per minute. Your ALEKS instructions will say, do not round intermediate computations, and then you are supposed to round your answer to the nearest whole number. Question A says, find the angular speed in radians per minute. The only formula that we have for angular speed is the one that says omega equals theta over time. We almost have this information given to us. Our theta is partly there because they tell us about revolutions. You need to remember that 1 revolution equals 2 pi radians. We are told that this fan is turning at 45 of those revolutions per minute. So we do already have our unit of time. So what we have to think about is that we are doing 45 of those 2 pi's. So we need to, just for omega, take 45 revolutions per minute times the 2 pi radians, because we are doing 45 of those 2 pi's. And when you say of like that, you multiply. As soon as you take revolution times radians, revolution goes away. So what we now have is 90 pi radians per minute. So that is our angular speed. We are in how many radians per unit of time. Your instructions in ALEKS say to round your answer to the nearest whole number. So if you take that 90 times pi, you're going to get 282.74. And then it says to round it to the whole, so we're going to say approximately 283 radians per minute. Part B of this problem says find the linear speed of a tip of a blade in feet per second. So if you just think about the single point that's on the tip of a blade, how fast is it making a circle in feet per second? Linear speed is the letter V. We have 2 formulas that have V in them. We have V equals S over T, or we have V equals R times omega. So what we have to do is think about what kind of information are we given in this problem. In order to use V equals S over T, you must know something about arc length. Nowhere in the setup of our problem do they tell us anything about arc length. So this formula is out. If we look at the V equals R omega, we need a radius. Well, we were told very specifically that the radius is 14 inches. And we just found omega in part A. So we are going to use the V equals R omega version of this formula. So setting this up, we will say V equals, our radius is 14 inches, and we take that times our omega. When you go to these second parts and you have to use answers from the previous part, do not use the rounded answer that you put in for part A. Go back to the 90 pi version of it. That's what those directions were saying, do not round intermediate computations. So 90 pi radians per minute is our omega. Now, as soon as I take a unit of length times radians, radians are gone. I don't have to worry about that. So what I have right now is 14 times 90 pi inches per minute. If you look at what we're supposed to be doing, it needs to be in feet and seconds. So those of you who have taken chemistry in the past, it's coming back to haunt you. We have to do conversions. In order to convert from inches to feet, we know that there are 12 inches in 1 foot. We need the inches to cancel out. So we're going to take this times a proportion of inches and feet, and in order for inches to cancel, it needs to be in the bottom. So we're going to have 12 inches in the bottom, 1 foot in the top. So now inches has canceled, and we have a unit of feet, which is what we want. Our time label needs to be seconds. We currently have minutes. So we need to use the relationship between minutes and seconds. We know that there are 60 seconds in 1 minute. This time we need the minutes to cancel out. So in order for it to cancel out, then it needs to be in the top. 1 minute equals 60 seconds. So now the minute in the bottom and the minute in the top have offset each other. So let's look at what we've got left. We've got 14 times 90 pi times 1 over 12 times 60, and then our labels are feet and second. So then if you multiply this all out, you get 5.498 feet per second, which, rounding to the nearest whole number, is 5 feet per second. On example 6, we are told a cyclist is riding a bicycle whose wheels have a diameter of 28 inches. She is traveling at 28 miles per hour. Question A says, find the angular speed in radians per minute. For angular speed, we have omega equals theta over t. So you have to know something about the angle. We don't know that at this point. Or we have the formula of V equals R times omega that shows how linear speed and angular speed relate to each other. The reason that I'm looking at this is because I need to recognize when I see 28 miles per hour, that is a velocity, that is a speed. So that is our linear speed. So I know V, and the other thing in looking at this, I'm told diameter of 28 inches. Well, that means that R has to equal 14 inches. If we want to find angular speed, we need to take this formula and divide both sides by R so that we have omega equals. So we have omega equals V divided by R. In order to make our problem a little bit easier to deal with, I'm going to use fraction rules and rewrite this as V times 1 over R. That will help us as we move forward and we have to do some conversions. Now that we know how we're going to find omega, what formula we're going to use, we're going to start putting things into position. Omega equals V. What is V? It is 28 miles per hour. I find it really, really helpful to write the units in full fractional form instead of with the slash. It makes it so much easier when you have to do conversions. We're going to take that times 1 over our radius is 14 inches. If you look at where we're trying to get, we are trying to get to radians per minute. In order to get to radians, here's the thing to remember. All of the units of measurement have to be gone. If all your units of measurement are gone, then you are down to radians. Your time will still be there as a time, but the units of length have to be gone. So we need to get rid of both miles and inches. We're going to go from inches to feet first. That's a little bit easier. So we know that 12 inches is 1 foot. Currently, inches is in the bottom. So in order to make it cancel, we're going to put it in the top, is 1 foot. By the way, when we're taking these times these fractions of 12 inches and 1 foot, even though they are not written in the same units, we are really just taking this fraction times a 1. And anytime you take something times a 1, you have not changed the value of it. So at this point now, inches are gone. That's good. The problem is we still have a unit of measure of feet and miles. You may or may not remember that there are 5,280 feet in 1 mile. Feet right now is in the denominator, so we want to put 5,280 feet in the numerator to make the feet cancel over 1 mile in the denominator. Well, now look what happened. Feet cancels with feet. The other thing that happened is that miles from way over at the beginning cancels with this miles. So let's look at where we are right now. We have 28 times 1 times 12 times 5,280 for numbers in the numerator. In the denominator, number-wise, we have 14 times 1 times 1. If we look at our labels, we have no more units of length. So we are into radians. Our unit of time, though, from way back over here is hours. Is that what we want? No, we want minutes. So we are going to take this times 1 hour equals 60 minutes. Now the hours are gone and we have radians per minute. Number-wise then, we have 28, I'm going to leave the 1 out, times 12 times 5,280 divided by, in the bottom, we have 14. I'm going to leave the 1s out because they don't have any effect, times the 60 from way over on the end. Our labels are radians and minutes. Well, this is the units we want, so we just need to do all the multiplication and division for this. And if you do, you get 2,112 radians per minute. It's very nice because this answer came out to be a whole number, so we don't have to worry about any rounding. For part B, we are asked to find the number of revolutions the wheels make per minute. If we go back to our answer for part A, we already know that we have 2,112 radians per minute as our angular speed. If you think back to our last problem, we talked about the fact that 1 revolution is 2 pi radians. So what we really need to do is just take this answer and get radians out of it. So we are going to use the proportion that we know and take this times 1 revolution equals 2 pi radians. Well, now the radians cancel, and you have 2,112 times 1, 4 numbers in the numerator. You have 2 pi, 4 numbers in the denominator. Your labels are revolution per minute. Do these calculations and you wind up with 336.14. But remember, we are supposed to round our answers to the whole number. So we're going to say this is about 336 revolutions per minute. All of you at some point will run into a problem that uses planets. In this particular problem, we're using Jupiter. What you will find is that the numbers are odd and they might be really big. So just a heads up. Our example says Jupiter rotates on its axis once every 10 hours. The equator lies on a circle with radius of 44.423 miles. So let's go back and just look at this information before we start. What you need to understand when they tell you this is that 1 revolution takes 10 hours. That's what you need to understand about that. And then this, the 44.423, is R. Question A asks us to find the angular speed of a point on the equator in radians per day. We aren't too far away because we know about revolutions. So remember what we said about a revolution. We said that a revolution is 2 pi. So I can just take out 1 revolution and replace it with 2 pi in 10 hours. So if we think about our basic definition of omega, angular speed equals theta over time. We know our angle, it's 2 pi. So we are going to have 2 pi radians divided by our time, which is 10 hours. So right now we are in radians per hour. Our label needs to be radians per day. So this is not a very difficult conversion. We only have one thing to do. We need to take it times how many hours in a day. We know that there are 24 hours in one day. Hours is currently in the denominator, so we need to put it in the numerator on our conversion fraction. So we're going to have 24 hours is one day. So now hours over hours have offset each other. And if you look at what we're left with, number-wise, we have 2 pi times 24 over 10 times 1. And then labels, we have radians and days. So that's what we need. Now we need to do the calculation on this, and we get 15.079 radians per day, but we need whole numbers, so it's about 15 radians per day. Question B asks us to find the linear speed of a point on the equator in miles per day. So we're being asked to find linear speed, which is v, And if you think back to our given information, we had an R. So what that means is that we are going to go back to this V equals R omega. So let's get started putting things into position. We were told that our radius is that funny number of 44.423 miles. We need to take that times our omega, which we just found. Now I'm going to use the decimal version to be 15.079 radians per day. They were kind to us on this problem. If you look, remember what I said, as soon as you take a unit of length times radians, radians falls out. And so if you look at the labels that we are going to have, we have miles, we have day, we don't have to do any conversion. So we are just going to take 44.423 times the 15.079, and then our label is miles per day. And if you do that calculation, you get 669.9 miles per day. But remember, we are rounding to the whole number, so this would be 670 miles per day. Our next example, we have a cyclist is riding a bicycle whose wheels have a radius of 15 inches. The wheels turn at a rate of 320 revolutions per minute. Question A asks us to find the angular speed of the wheels in radians per minute. This is similar to a problem that we did earlier. Anytime that you start talking about revolutions per, you are very close to having your angular speed, because we know that one revolution is 2 pi radians. So we are doing 320 of those. Our angular speed then is 320 revolutions per minute times the 2 pi radians that each revolution is. Remember, as soon as you have radians, revolutions goes away. So if we take the 320 times 2 pi, we are going to get 640 pi, and then our label is radians per minute. If you do that on your calculator, you get 2010.6, which we are going to round to be 2011 radians per minute. Question B asks us to find the speed of the cyclist in miles per hour. First thing you need to recognize is that as soon as you see speed, that means V. We want our label to be miles per hour. And if you think about the information that we know the radius. We know that the radius of our wheels is 15 inches. And we just found from part A that omega is, now we go back to the pi version of this, 640 pi radians per minute. So the formula that we want to use is the V equals R omega. Our R is 15 inches. So we're going to have 15 inches. We're going to take that times 640 pi radians per minute. Well, as soon as we have a unit of length, radians is gone. So that's taken care of. Look at what we want for our label. We need miles per hour. So at this point, we have 15 times 640 pi, and we have inches per minute. Let's convert the hours. That will be quick and easy. So we need to get rid of minutes, make it hours. So we are going to do 60 minutes in the numerator is 1 hour in the denominator. So now the minutes are gone. Looking at what we have now then, we have 15 times 640 pi times 60, and we have inches per hour. I'm not going to write the divided by 1 because that doesn't have any effect on anything. Just for space purposes, I'm going to go ahead and multiply what we have at this point. Our number is big. It is 57630, so 576,000 pi, and we have inches per hour. The problem is we need miles, so we need to get the inches out of there. So we need to do 1 foot and 12 inches. Inches need to go in the bottom. So now inches is gone. Problem is now we have feet an hour. That's not right. We need miles. So we are going to do feet and miles. In order for feet to cancel, it needs to go in the bottom. 1 mile is 5,280 feet. So now feet is gone. Now we have 576,000 pi times a 1, which doesn't have any effect, divided by 12 times 5,280, and our label is miles per hour. If you do that calculation, you get 28.6, which we need to round to the nearest whole, will be 29 miles per hour.